In this section, we want to generalize the notion of higher order derivatives to the case of functions in several variables. Previously, in Mathematics 1, we have just derived functions on intervals and have just taken derivatives of derivatives and so on, because derivatives, in case of differentiability, were again functions, which we could derive again and again and again, and so on. Now, with our knowledge so far, I mean, there is a way to generalize this also to abstract vector spaces and so on, but I won't go that far here. But from what we've learned so far, it's not that obvious of how to generalize these things. Namely, we've seen that the differential at a point is a linear map. So it's no longer just a number that we can associate, but the differential associates with every point of a differentiable function a differentiable linear map. So the question is kind of what's the, we can't say what should be the derivative of this now at this point, but we want of course to formalize some notion of differentiability and so on, and we have maybe some ideas in mind of what's going on. Remember, we've seen that the differential of a map basically incorporates all directional derivatives. If we insert a vector into this derivative, if we insert a vector into the differential, we obtain the directional derivative in that direction. Now, in the higher dimensional setting, we of course want to include kind of all, in higher order setting, we want to include all higher order directional derivatives, namely directional derivatives by v1 followed by directional derivative by v2, for example, for the second differential, and also all the partial derivatives of higher order, which we've already seen. The second order partial derivatives should all be part of the second differential somehow, and the same for kth order differentials. If we just iterate, we want all of them basically one big object. But the question is then, of course, what should this object be? What should it look like? Now, we solve this by introducing some new linear algebra and a new kind of object that we haven't seen so far, which generalizes the notion of linear maps in some sense, and then see that this is the correct notion, and in this way we will then formulate the notion of differentials of higher order by applying this linear algebra part to a particular situation. As I've mentioned earlier, I will not do the most general notion of differentiability in here, because this would just take way too much effort, and it's more complicated, so it would be a bit more tedious to do so. So let's keep it down to kind of something which is, where we still stay, where it stays nicely understandably in Rn, and so, I hope this is fine for you. Now, in order to go to differentials, let's introduce a bit new linear algebra. Here we will introduce some new notion from linear algebra and study it in greater detail, or part of it in greater detail in the next section, but this will be only little bits and pieces from linear algebra at this point. Okay, so in a general case, let K be a field. You missed it, didn't you? Let V and W be vector spaces over K. And let N be a natural number, such that N is 2 or bigger. Now, A, if we take a map F from the nth power of V, meaning we take V times V, so the Cartesian product of n copies of V. So here we take Vn times to W. Such a map is called n-linear. And n-linear, and one simplifies this notion. So in the case of n equals 2, you don't write 2 linear, but the word that's used then is bilinear for n equals 2. Also for n equals 3, sometimes you use the word trilinear. And I think it's also the notion of quadrilinear maps and so on, but we won't go too far. We will only need the bilinear maps in the rest of this lecture explicitly. So a map is called n-linear if for all I between 1 and n, basically the idea is that f should be linear in the ith component, and this looks maybe a bit familiar to you because we have seen examples of this before, as I will mention in a bit. So for all I in n and for all vectors v1 to vn and wi in v and all numbers, yeah, let me squeeze this in there, lambda and mu in the field K. If the following holds, if we take f of v1 and so on to vi minus 1 and assume in the ith component we have lambda vi plus mu wi, and the rest is just vi plus 1 to vn. So we want linearity in this component, so you might guess what's coming now. This should be the same as lambda times f of v1 to, and now vi minus 1, and now it's just vi in that component, to vn, plus mu times f of v1 to vi minus 1, and then wi in the ith component, and in the rest we just have the v's again. So it kind of behaves well with respect to addition and with respect to multiplication by scalars. If we just fix all entries except for the ith one, it's a linear map, and this holds true in every I, so for ith components. Sorry, I was a bit quick and skipped a part of the definition in the first attempt. So this is an n-linear map, and we further put Ln from V to W to be the set of all n-linear maps from V to W, Vn to W. F is n-linear. So you could basically receive, if n is equal to 1, basically you would get the definition of a linear map. So we had just denoted the set of linear maps from V to W by L of VW, so this is just generalizing this notation in some sense. Okay, this is the set of all linear n-linear maps. Then a special case. If the target, so the codomain, if this is just the field, so if we're just mapping from Vn to the field, an n-linear map f from Vn to k is just called an n-linear form. If you recall from the section about dual spaces, I have also said that linear maps from V to K are also sometimes called linear forms. So this is just generalizing this. And in the same way as before, we say bilinear form for n equals 2. And this is the notion that we will need later on. In the same way, you could get trilinear forms and so on and so on. But bilinear forms will be important later on. And finally, we just call a map, if we just don't want to refer to n-linear all the time, a map is called multilinear if it is n-linear for some n. So if I'm talking about something multilinear maps, I'm just talking about all of these, basically all of them collected. If it is n-linear for some n bigger than or equal to 2. Okay, this is linear algebra, and maybe you might think this looks a bit familiar, and the reason is we've already seen examples of multilinear maps. And let me just repeat, I'll give you a very simple examples and a very simple explicit example, and repeat some of them that were already part of this course. Namely, first of all, if we take the map which goes from Rn to R, and this time we just view R as a vector space over itself. So this is R times R times R, n copies of the real vector space R. And if we take the following map, f of x1 to xn, is simply the product of all the entries. x1 times x2 times and so on times xn. This is not a linear map, but this is n-linear if we view it as a map from the real nth power of the real vector space R. So this is n-linear, which means in this notation from above, F is a n-linear map from R to R. This is how you would write that. And that's easy to see. If I would just, in every component, if I would multiply things with constants and so on, we can factorize the constant out of the product. And also if I have a sum in there, if there would be xi plus yi, I could also use the standard multiplication rules to get the two sums, which would then, so the equation that we need for this is a very easy computation, so I will not do this, and this is easy for you to carry out if you don't see this immediately, but this is really not that difficult. Okay, so this is, for all n and n, of course. So, or n bigger than or equal to 2. Okay. Secondly, we have discussed already an example of bilinear forms, namely if V is a real vector space, then any inner product so from V times V to R is a bilinear form. And this is what we've already seen. Namely, in the first component, that the linearity in the first component is part of the definition. And the linearity in the second component, this already follows, I think we formulated this as a remark when we discussed about, inner products. Then, so the linearity in the second component follows from the linearity in the first component and the symmetry of the inner product. So this is, this is what we've already seen, so there's nothing to compute in this, at this point. So very formally speaking, this would be a bilinear map L2 from V to R. Another example of a multilinear map where I've already used the multilinearity, the word multilinearity, namely the determinant. I've started by discussing the determinant, not of matrices or of linear maps, but of tuples of vectors. Namely, we had elements of Rn, for example, so let's do this in Rn, to the power of n to R. And this map was multilinear. This was part of the definition. Again, the arguments here are now n vectors, and later on we've defined the determinant of a matrix by discussing the column vectors and so on. But this is how we first started defining the determinant. So this was section 9.1, is n linear. This is by definition. If you take it, the property in definition, which I think already called multilinearity at that time, this is precisely what we need there. So this is, this follows from the definition of the determinant. And so to be precise, that would be an element of Ln, the space of n linear maps from Rn to R. So it's really Rn to the power of n. This is a multilinear map as well. Okay, one more example that we've seen in the exercises, namely the vector product, which you probably also know from your physics classes. So this, in the exercise, we get it for three-dimensional vector spaces. That's a general construction. Let me now just discuss the one in R3. So the vector product. So which any two vectors which are linearly independent, we get a third vector which is linearly independent to both of them and orthogonal to the plane spanned by the first two vectors. This vector product here, this is bilinear. So this was already part of the, I've defined this axiomatically in the exercises, so it's part of the definition. And this was, which exercise was this? Sheet 8. Exercise 3, this is bilinear as well. So, to denote this, so here we have two entries, which I represent by dots. This as a map is a bilinear map from R3 to R3. Okay, this is just the, by definition of this inner product, of this vector product. Okay, now, the idea is now that we want to define the nth differential of a map as an n-linear map. This is, in that sense, generalizing what we did with the first differential. So, how do we do this? And this is combination of theorem and definition again. 1248. Now let m and n be natural numbers, u in Rn open, and f from u to Rm be k times continuously differentiable, as we've seen in the last section. So all kth order partial derivatives exist and are continuous, continuously differentiable, where also k is some natural number. Okay, then for each point, so for each a in u, the map, which we define as dkf in a, so this would be the kth order differential. So what does this map do? This map takes k vectors from Rn. So it's a map from a subset of Rn to Rm. So here we take Rn to k and go to Rm. So, and what do we do? dkfa of v1 to vk is defined as the iterated directional derivative, namely dv1, dv2, and so on, dvk f in A. This is well defined. Since f is k times continuously differentiable, then we can express all these guys in partial derivatives and see that everything is continuous. Everything is differentiable, and yeah, so here we can just use these properties here. And this map that we can construct in this way is k-linear. So first of all, this is called the kth differential of f in A is k-linear. Okay, so this is really this is the definition part here. This is a k-linear map, as we will see soon, and this is not the end of the theorem and definition, but I've run out of space. So there's also an explicit formula how we can express this in terms of partial derivatives, which I will do next. This is what we've already seen for the first order differential. So for the kth order differential here, we can then, again, have a formula for computing these guys, as we shall see after erasing. I forgot to mention one little thing. This map shall be linear, and this is the way it's defined, but of course we haven't defined directional derivatives if the vector is 0. But here we use a simple convention here, and basically all the time when we're in this situation, we say that the directional derivative by the 0 vector of an arbitrary map G in A, so it might already be an iterated directional derivative or something, this is just defined to be 0. Meaning if one of these vectors is 0, then the directional derivative of the part by 0 of whatever is coming afterwards is just 0, which means the whole thing is 0. So whenever one of these vectors is 0, the kth differential is completely or is 0. Okay, so this is the convention there. So we need to show that this is k-linear, and moreover, we need to show, or we want to see the following equation. The kth differential of f in A of vectors v1, v2 to vk. This is the following, and I think I'll need more space to the right than I have. So namely, we take a lot of sums, namely for each index from 1 to k, we take a separate sum. So the sum from I1 is 1 to k, the sum from I to n. I2 is 1 to n, and so on, until we get the sum ik is 1 to n. And then we take the kth order partial derivative, which we get by just following the indices here, namely the derivative d, I1, I2, and so on, ik, f in A. And now I need a lot more space, or not a lot, but more space. So please remember this was the shorthand notation for first taking the derivative in ik direction, then ik minus 1, and so on and so on and so on, until we then take the I2 derivative and the I1 directional derivative in this direction. So this is the k-fold partial derivative, and now the role of these vectors is just again taken by multiplication with the entries of the vectors. Namely, if we denote the entries by Vj is Vj1, Vj2, and so on to Vjn for all in Rn and for all j from 1 to k. And then the idea is now that from each of the k for each of the k directions, we just take the corresponding component corresponding to the index of the vector that corresponds to it. So from V1, we take the I1 component and multiply this here. And so we multiply this with Vi1, 1, other way around, V1, I1. Then we take for the second derivative, there we have the I2 direction, so it's V2, I2, and so on. And multiply finally with Vk, Ik. Okay, a little like this. But this big equation here holds, and this means, this looks awful, but this is something we can compute. We can compute partial derivatives with our standard rules of derivation, so we can, this is not that hard, and this is just multiplication with some numbers. So, this is a bit tedious to do this by hand, but this is something you can feed in a computer. So you have the standard rules, you can find algorithms that do this. So this is the way we can describe these higher order differentials in a computational way. Okay, now, this is the statement. So the statement was, because the first part of it is already gone. So the statement is this map dkf is defined like, which is defined like this, is k linear and has these and satisfies this equation, which I shall call star in the proof here. So, and the first observation is it suffices to prove this equation star, because if once you have this equation, this already implies the k linearity, because you can check this from that component. The crucial part is that here in this product, there's precisely one entry from each vector, and if you do a little computation, which I recommend you to do so by yourself to scribble a bit on a notepad, there you can see that this really it turns out that this expression here on the right hand side, this is really k linear. Just by doing some algebra, and I kind of recommend you to pause this video and check this as a computation for yourself now. So we will only check this, so then if we have checked this equation, then k linearity follows. And the proof will be done by induction, so induction over k. The good news is the base case is again trivial, or not trivial, but we've already seen it. Namely, the base case of k equals 1 in this setting. This is just a corollary that we had. Corollary, what was it? 1217. Namely, the differential, so for k equals 1, we just get the differential as it was. dfa of v is the sum from I from 1 to n di f in a times vi, the ith entry of the vector v. Sorry for squeezing here, but this was what we had seen in this corollary already, so this is what we already know. Now, for the induction step. So we assume as induction hypothesis that for some k, bigger than 1, and namely what we do is now we do not assume the induction hypothesis or the statement for k and show the statement for k plus 1. Instead we assume the statement for k minus 1 and show it for k. This is the same, but this is a bit more convenient with the notations here in this setting. So that for some k equals 1, it holds that dk minus 1 f a of some vectors v2 to vk. So this is just for nice notation. We just label them starting with the second one, and we will later see that this turns out nicely. So then the hypothesis must be the following. We have, this is already given as the sum from I2 equals 1 to n to the sum of ik equals 1 to n of the partial derivatives di2 to ik f in A times, now losing space here again, v2i2, v3i3, and so on, vk ik. Whoops. And this for all vj equals vj1 to vjn, and now j is between 2 and k. This proof is really a bit tedious to write down because of the lengthy formulas here. So this is our induction hypothesis. Then, so assume we have this formula already. And first of all, it's important to notice, since f is k times continuously differentiable, this means that all derivatives of, so partial derivatives of order k minus 1, for example these here, they start with 2 and go to k, so this is k minus 1 times. All of these derivatives, so all of the di2, i3 to ikf, they are, again, continuously partially differentiable and hence differentiable. So these, sorry, I hadn't fixed the camera properly, so the camera just went down and went out of focus, so I had to fix everything again. Sorry about that. So we know that all these derivatives are differentiable. So this means in particular that for all of these derivatives, we just make now one computation which will be helpful then. Thus, for all I2 to ik between 1 and n, we compute the following. If we take the directional derivative by some v1 of di2 to ik of f in A. Now these are differentiable, so we know by Theorem 1215 that this is the same as the differential of di2 to ikf in the point A evaluated at V, and this is by corollary 1217. The same as the sum from I1 equals 1 to n of di1, so this derived here by, so di1 of this expression, which of course we can then write in the shorthand notation as di1 I2 to ik of f in A times the component of v1, which I shall label as v1 I1. And this holds for all v1 equal to v11 to v1n in Rn. Okay, this is what the differential does. So let's keep this equation in mind. Maybe, yeah, let's label this as 2 star. So 1 star was the big formula above. So now we are ready to do kind of the eventual computation of the induction step. Namely, we have seen, so please recall, this was here the assumption. So what follows for the kth order differential? So we know that dkf of v1 to vk in the point, in A of v1 to vk, this is by definition just dv1 to dvk of f in A. But this can of course be written as, and now this is where we want to bring this back to the induction hypothesis, as dv1 of dv2 to dvk of f in A, but this here is by definition the same, so dvk of dk minus 1 f in A of v2 to vk. And this is now a bit confusing maybe. We view this as a map in the variable A, and they take here the derivative there as an abstract object. Now, it doesn't matter really what, how this looks like in detail, but this is what this means. But for this, we have the induction hypothesis, and we can express this by this big sum. So, by the induction hypothesis, this is the same as dvk of the sum from I2 equals 1 to k and so on, to n, and so on to the sum of ik equals 1 to n, di2 to ik f a, and then we have v to I2 to v k I k. Okay, now we can use the properties of derivatives, namely we know that they're compatible, so directional derivatives, we have seen that they're compatible with sums, and these are just constants, these are just numbers with which we multiply this partial derivative vector. So again, we can multiply this there, and so we can use the compatibility rules and get that this is the sum of I2 from 1 to n and so on to ik from 1 to n of dv of di2, sorry, dv1, I've written vk, sorry, v1, not vk. Vk was included in there. Same here, sorry about that. So dv1 of these functions here, so I2 to ikf in the point A times v to I2 to vk ik, and this is precisely what I've computed here. And for this we can just use that simple formula, which means that by that formula, 2 star, we get that this is the sum from I2 is 1 to n to ik is 1 to n of the sum I1 is 1 to n d I1 I2 to ik f in A times v 1 I1. So this is what we get in there. And now we just have to reorder the sums, because it turns out because everything is associative and commutative and distributive, so everything works out nicely. So we can just reorder and reorganize everything. So this is the same as the sum from I1 is 1 to n over the sum from I2 is 1 to n, from until ik is 1 to n, di1 to ik of f in A times v1 I1, v2 I2 to vk ik. And this is what we wanted to show in the induction step. And so this shows the formula here. Let's compare. This looks good. This is the same as I've written there. So we've really proven the induction step, shown the induction step here. And as I said before, this already leads to the k-linearity of the kth differential. And yeah, I invite you to really check the details of this linearity there. Okay, this looks very complicated and tedious, and we will see a simple example of this after I erased. These higher differentials are quite confusing when you see them first, because you get these enormous formulas and you think, okay, this must be very hard to compute. So the good news is it turns out if you're in low dimensions, like if in the subset of R2 or R3, this is usually relatively concise to compute, and we shall see a detailed example at the end of this section. But first I want to show you some example where it takes a very simple form, namely, I'll do this as a remark. This is remark 1249. So, in the case of the second of twice continuously differentiable function and the second derivative of such a function. So I'm just using the notation now from the previous theorem. So, so in theorem / definition 1248, then it becomes a bit simpler. The explicit formula becomes, and now let's take a look. So assume we have D2f in some point A, which is now a subset of R2 by construction. So what we include here is two vectors from R2. So let's do it as V1, V2, W1, W2. Okay, these are two vectors inserted. So by this description there in terms of partial derivatives, so this would mean in this special case we would have the sum as I1 goes from 1 now to n, but n is 2, so we just have the sum of 1 from 1 to 2 and the sum of I2 from 1 to 2 di1 I2 f in A, and now we have v I1, and now instead of, I've changed the notation here slightly, so instead of V1 and V2 for the vectors, I'm now labeling the entries here as V1 and V2 and W1 and W2 there. So this here gives the entry of the first vector, and this here the entry of the second vector, meaning we get Wi2. Okay, now this is much ado about nothing, because this is, if you take, these are just two summons. It's almost not worth writing a summation sign there. And if we have two summons here and two summons there, in total we have 2 times 2, which is 4 summons. And so we can just write them down explicitly. Namely, the first case, when I1 and I2 are 1, we get D1, 1f in A times V1, W1, okay. Plus, now that E1 equal to 1 and E2 equal to 2, then we get D1, 2f in A times V1, W2. Okay, now that's I1 equal to 2 and I2 be equal to 1, then we get D2, 1f in A times V2, W1 plus, and now both are equal to 2, D2, 2f in A, V2, W2, and so this is everything. And we can still simplify some things because we know that these two partial derivatives, by Schwarz's theorem, these two coincide. So we can also summarize this. So Schwarz then tells us that this is D11f in A, V1 W1 plus D12f in A, V1 W2 plus V2 W1, written like this, plus the final summand D2 2f of A, V2 W2. And these V and W are just numbers. There's nothing fancy about them. So all we need to do to compute the second differential there is to compute 3 partial derivatives here. So 3 second order partial derivatives. Of course we need the first order partial derivatives first, but this is something, this is doable. So this is something that you can now write down by just computing those numbers for some examples and then multiplying with the right numbers. Okay, let's do a very simple example of that, of exactly just that. So example 1250. Now f is a map from R2 to R, and a very simple one, namely f of x1, x2 is x1 squared plus x2 squared. Doesn't get much simpler than that. Okay, we've seen already the partial derivatives of this. This we already had as a simple example of partial derivatives, namely d1f, x1, x2, and now that we kind of really understood partial derivatives and how to derive them, this is almost trivial. This is 2x1 by the standard computational roots. We have shown this explicitly from the definition, but now by our understanding of derivatives, this can be read off precisely from the expression here. And the second partial derivative, d2f in x1, x2, is 2x2. Sorry about that. If we take a look at them, these are again, so the DIF are continuously partially differentiable. So this means f is twice continuously differentiable. And we now compute the second order partial derivatives. So to get d11f in x1, x2. So yeah, what's there to do? We need to derive this by x1, and this is obviously just 2. d12f x1, x2, which is of course the same as d21 by Schwarz's theorem, meaning we need to derive this by x1, but there's nothing of x1 left, so this is just 0. And finally d22f in x1, x2, and similar as for d11, derive this by x2, and all you get is 2. This means if we insert this now in this formula that we have here, that this becomes even simpler. So this derivative here is 0, so this entire thing vanishes, so everything that's left is here and there. So this means the second differential of f in some point x1, x2, if we evaluate this on two vectors v1, v2 and w1, w2, so this is always, and it turns out that all the partial derivatives are not depending on x1, x2. This is of course not the case in general, but here it's particularly nice. So here we get that the first derivative is just 2, v1, w1, 0 for the middle part, and at the rest we just have 2, v2, w2. This particularly gives the same map for all x1, x2. This is unusual, of course. So this holds for all v1, v2 and w1, w2 in R2. So this as a map is the second differential, and of course by construction we just get the directional derivatives then by this formula. So all second order directional derivatives then there. Okay, now so we've established these higher order derivatives, and in the same way as we did in the last semester for single variable function, we will now want to use derivatives to approximate functions. Namely, we want to establish a multidimensional Taylor theorem. The idea of Taylor's theorem in the last semester was that we could kind of define polynomials, the Taylor polynomials, so a polynomial of degree n by using the first n derivatives of a function, to get a polynomial which is kind of the polynomial of degree n, which is kind of the best approximation for the original function. We still didn't know if it was good, or it's a good approximation, and if the function is convenient for being approximated by polynomials, but we could find, we could do this in many cases and could find nice polynomials that up to a really small number or something represent the function. So in other words, we could represent, approximate a very complicated function by a polynomial, which is a very simple function. So this could then be used, and this was the motivation I gave you, to really compute approximate functions approximately, which are otherwise very hard to compute, because polynomials, also by computers, they can be performed by just elementary operations. You just need addition and multiplication, and you can describe all the polynomials, and you don't need any fancy or more elaborate constructions from mathematics. So this really turns out to be useful in some points. The good news is the same thing can be done in higher dimensional setting. We can now, we have developed the notion of polynomials and n variables. This is what I defined in the previous chapter, and if you don't recall this precisely, now is the time to look it up. So we have polynomials and multiple variables, and we can again take some differentiable function in n variables, and this time we only study functions with values in R, so maps from Rn to R, or a subset of Rn to R, and to take their higher differentials to really then again approximate something by polynomials. Of course, the formula becomes a bit more abstract, as you might have been afraid of, but let me show you it's not that complicated, and I will first do basically the abstract things, and then give some computation in between, and at the end we will see an example where I will compute some Taylor polynomial explicitly. Okay, now, a long monologue before, but now let me give you straight away the definition of these Taylor polynomials. So, before, maybe I could squeeze this here in the corner. So, the Taylor polynomial Tnf of x in a point A would be defined as the sum from k equals 0 to n of the kth derivative of f in A. Oh, now this is a bit, I need more space to squeeze here, sorry. Okay, let's start over here. Tnf of x in A. So if f is a function defined on an interval, a real function defined on an interval, this was the same as the sum, or this was defined by the sum from k equals 0 to n of the kth derivative of f in A divided by k factorial times x to the k. Actually, I've used a slightly different notation in the previous semester, namely this would correspond to x minus a to the k here. I'm shifting notation here slightly. I'm sorry if this is confusing anyone. I've put a little explanation also in the lecture notes. The conventions I will use now are a bit more convenient and a bit more easy otherwise, so it's easier to use here and you get nicer formulas. So, but this was the general idea. Here we compute the derivative of a function at a point, divide by this factorial then, and here we get just x to the k. So in that sense we get a polynomial whose coefficients are determined by the derivatives. Okay, and this is basically the same thing that we will do now in the higher dimensional setting, but we just need to find a suitable replacement for these numbers here. I mean, this is just a number. And now we have these n-linear maps, which are just so differentials, and so we need to find the analog of this description. But it turns out there is really an analog which is not that complicated after all. So let k and n be natural numbers, u be an open subset of Rn, open, and f from u to r be k times continuously differentiable. So here I'm really studying only the case that will map to R. So k times continuously differentiable. Okay, and again, so the idea was here that this is a good approximation of the map by a polynomial in some close to the point A, in the neighborhood of the point A. And the same we have here. We cannot expect to have an arbitrary complicated function and approximate this by a polynomial, but we can always do this locally around a point, so in the neighborhood of a point, so to say. And here as well, given a point A in U this time, so a point in Rn, we call the following map the Taylor polynomial, and this is tk of f, and here's the variable inserted x or v or whatever in the point A. This is now a map from Rn to R, and tkf in VA, so V is now, I'm using the vector definition, or the vector notation here, V an element of Rn. So how do we get this? This is the same as the sum of all, slight definition, sorry. So the first one is just f of A. This would correspond to the summand from k equals 0 to n. This is for k equals 0 in this setting. f0 is just f itself. So a little more space. For the derivatives, we take the sum from r equals 1 to k, and now we take the rth derivative of f in this point A, but what do we insert now? This is a multilinear map, and we cannot just take a variable and multiply it by this value. Instead, we take this map and insert just v r many times. We put v in every slot and divide this by r factorial. So this expression here turns out, as we shall see in a moment, to be the generalization of taking x to the k and multiplying this with the derivative here. So this is also taking x k many times, so to say. And here we take the vector v k or r many times in this notation. So this generalizes in that way. And this is called the kth Taylor polynomial. Of f in A. Okay, now from this formula, this is very concise, very abstract, okay, but here it's not easy to see, or it's almost not visible, that this is indeed a polynomial. So why is this a polynomial in variables? We can basically just do the dirty computation and prove this. Namely, we can simply use In the same way as we proved before, this expression of the higher differentials in terms of partial derivatives as these huge sums. Then it turns out that these expressions will become polynomials in the components of V. So namely in the following form. So again, sorry, let K, N, F, and so everything be defined as there. In this setting, so using the explicit formulas for DRF A, as we've introduced them, the higher differentials here, we compute for any vector v1 to vn in Rn, so some element of Rn. Yeah, now I have to remove this single variable one. Okay. If we just use these formulas, then what stands there? So if in every expression, so every dr, we replace by the corresponding sum, this huge sum from before. This gets, of course, a horrible expression. But this looks as follows. Tkf of v1 to vn in the point A. This is now, so let's keep f of A plus a sum from r equals 1 to k. And now we get the sum, from I1 equals 1 to n to, and now since we have dr, we get to IR from 1 to n of, and now insert this 1 over r here, and then we got the derivatives di1 to IRF in A, and now what to multiply them with? In this huge formula, which is not visible on the blackboard anymore, there we had seen that for each ij, we take the ij component of the jth entry. But the ij component of the jth vector that is included here. But they're all the same. So all we need to do is to take the corresponding components of v itself, so of the vector v1 to vn itself. So for I1, we need to take the I1 component of V, so VI1, then VI2, and so on, to VIR. Okay, this is now a huge sum, and as soon as the numbers become bigger, this is horrible to compute. But anyway, it's possible to compute. That's the idea. So you could feed a computer with the data so that a computer could compute this. But what's the important thing here is, if we take a look at this, these are just numbers. These don't depend on the vector v, v1 to vn. This is just some coefficient here. This just looks frightening, but it doesn't matter. This is just some constant term. And v is only appearing here, but we only have products of entries of the vector multiplied with some constants and then summed up. This is by definition a polynomial. This is what a polynomial does. A polynomial in entries consists just of any products of these elements here. Of course, some might be the same, so we might have squares in there and so on, but products of the entries of the vector and multiply them with constant terms and sum them up. By definition, this is a polynomial. So this shows that TKF in the point A, seen as a map from Rn to R, is indeed a polynomial and what's the degree? So the degree, I mean, what's the highest product that can appear here? The highest is for R equals K. So we have K, the product of K elements. Of course, the kth partial derivatives might all be zero, so that we would have in K order terms. So what we can say is it's a polynomial of degree smaller than or equal to K. And this is, in that sense, generalizing this approximation by polynomial idea. Okay, now, this is now just the definition of the polynomials, and to show that we have really this approximation property, we need analogs of Taylor's theorem for the multidimensional setting. I have to erase now because I need more space, but in general, the idea is now that first of all we will show kind of a Lagrange form of Taylor's theorem. We had the Peano form and the Lagrange form in the previous semester, and we will basically again use the one-dimensional case to prove the higher dimensional case, and then see a Lagrange form of that theorem, and then go on towards a Peano form, and in the end see an example and of these approximation properties. Let me erase, and then we'll do Taylor.